Welcome back for our final lecture on nuclear materials, lecture 7. Today we'll look at corrosion alone, more specifically the corrosion of structural components, from stress corrosion cracking, irradiation assisted stress corrosion cracking, radiolysis of water through to segregation and its effects on corrosion rates. Now there is of course a wide range of components across a reactor, and each component will suffer its own corrosion problems, such as the irradiated stainless steel bolt shown in these images here on page 76. Here you can see the cracking indicative of stress corrosion cracking, like a river run, and I'll talk about that later. Given we don't have much time as we may like to cover everything, for this part of the course we're focused specifically on corrosion phenomena enhanced by radiation, especially irradiation assisted stress corrosion cracking. So let's go through some of that terminology. What is stress corrosion cracking? Well, it's cracking under the combined action of stress and a corrosive environment, where corrosion or cracking would not be expected should only one of those factors be in action. Okay, so you have to have the combination of both of those. Such cracking is actually only found in alloys. You wouldn't find it in pure metals, ultra pure metals. It's strongly dependent on composition. And each alloy itself will only suffer stress corrosion cracking in certain environments, with the stresses involved being residual, applied, or a combination of both of those. And that cracking can be transgranular or intergranular, as shown in the image at the top of page 77. Intergranular cracking is far more common than transgranular, with a fracture surface similar to that shown in image 2 on this page, showing those. You can see the individual grains, so that's indicative of intergranular cracking. But stress corrosion cracking is quite easy to identify, really, when you're looking down a microscope, on account of the unique river branching that I just mentioned. You get these river branching patterns of cracking, and that's what you see in the bottom image of this page here. That is indicative of stress corrosion cracking. So if you see that on a microscope, you've done your job as a metallurgist. Or rather, you haven't done your job as a metallurgist because you've chosen the wrong material. Now, one of the most interesting things about alloys that are susceptible to this kind of stress corrosion cracking is that they're often alloys that are intrinsically corrosion resistant, or regarded as corrosion resistant. It's only when you add stress that these things fail. So simply running a stress-free corrosion test will in no way represent what a component might behave like in operation. For example, if you were to take a 18 weight % chromium stainless iron nickel alloy, its stress corrosion susceptibility is greatest for 8 weight % nickel, despite the fact that that composition is the one that shows the greatest general corrosion resistance. So you can choose a super general corrosion resistant alloy. It turns out that might actually be the worst you could possibly choose in terms of stress corrosion cracking. So you have to do stress corrosion cracking tests. You can't just do stress tests and corrosion tests. So why? Well, let's talk about the mechanisms by which the cracking occurs. Now, cracking typically occurs in 2 stages: initiation and propagation. Once initiated, cracks will grow at a slow rate until the stresses in the material reach the fracture stress. And when they reach the fracture stress, fast fracture occurs, so you get failure. And alloys will show different resistances to those 2 different stages, initiation and propagation. Some may be highly resistive to initiation, but if they're already cracked, so pre-crack samples, for example, they'll propagate at a significant rate. So you have to account for both initiation and propagation when designing these. So how do these cracks occur and how do they grow? Well, stress corrosion cracking is widely considered to involve anodic dissolution at the crack tip, removing metal at the tip. And that's what allows the crack to grow. But in order to have such dissolution, you've got to have the current density at the crack tip, so all the current concentrating at the crack tip has to be higher than on the walls of the crack. Yeah. So the crack tip current density is higher than the current density on the crack walls. Otherwise, you would just get crack blunting. It would no longer be a sharp crack. So it wouldn't propagate. Now, as we know that general corrosion-resistant alloys can be highly susceptible to this stress corrosion cracking phenomenon, and corrosion resistance is typically governed by the formation of passive oxide films, then we can quite confidently hypothesize that it's the disruption of those passive layers, those films, that causes a susceptibility to stress corrosion cracking. And it's that disruption that I present in the graph below on page 78. If you look at the graph, you can see slip in the metal. And that slip breaks the oxide layer, revealing the fresh, unpassivated metal underneath. Now that fresh metal will then suffer rapid corrosion before repassivation can occur. And the rate of that repassivation is what's critical in how an alloy cracks. Should the repassivation rate be very fast, then you're not going to have a lot of corrosion occurring, so we don't lose very much metal. It just very quickly repassivates. So that's not too bad. You still have a sharp feature, but you've had very little corrosion occur. Although the crack is still sharp, so it could propagate under additional stress. Let's look at the other extreme, a really slow repassivation rate. Well, if the repassivation rate is very slow, we lose a lot of metal as you have significant corrosion occurring. But the crack will end up being blunted as a consequence of that large amount of metal loss, which will in turn limit the crack's propagation, as the stress is going to be distributed across the greater area of the larger crack tip. So actually the worst case is somewhere in between those two extremes, the high and the low. An intermediate passivation rate is the problem. Because when you have an intermediate passivation rate, you're at most risk of stress corrosion cracking because you have a fair amount of corrosion occurring, so you're eating away the metal, but not excessive enough to blunt the crack, making it still liable to propagate further. So it's still a bit sharp, but you've also lost a bit of metal. So stress corrosion cracking would involve the breaking of this oxide film, followed by corrosion, repassivation, breaking, corrosion, repassivation in cycles, repeating in cycles. And that's how you get this river branching of the stress corrosion cracks. So intermediate repassivation rates are the problem. So you need to make sure you understand that. But let's look at each stage in a little bit more detail then. So we need to make sure we understand this. So first we have our plastic flow. Okay? And this can occur in different ways depending on how easy it is for cross-slip to occur. Should your alloy have a high stacking fault energy, dislocations can easily cross from one slip plane to another. Should the stacking fault energy be low, cross-slip would be far more difficult, and that would lead to localized slip on planes that have active dislocation sources or low barriers to dislocation glide, meaning that the slip steps are going to be far greater, and that is what's going to promote stress corrosion cracking. So to give you an example, take stainless steel. Well, what happens if you add nickel? What happens if you add nickel? What does it do to the stacking fault energy? Well, it raises it. Adding nickel raises the stacking fault energy, which causes slip to be more diffuse. Okay, and when you've got more diffuse slip, that leads to an increased time to failure. So you've got a better resistance to failure. All right. And should you wish to depict this stress corrosion cracking graphically with the dissolution of the crack tip, here is a graph, or rather a schematic for just that. So should you be able to recall this and the previous image here, so these two images, if you're able to recall these individual images, you should be able to recall the individual stages of stress corrosion cracking. And should you be asked a question in your exam on stress corrosion cracking, you will be fine. But I haven't mentioned radiation yet, have I? So where is radiation involved in all of this? Well, going with the trend, it makes things worse and introduces some unique phenomena not seen in irradiation, in the absence of radiation. Unfortunately, it's rather complicated, and we don't know for sure exactly how radiation affects stress corrosion cracking. Because it varies significantly across different alloys and environments. So what we do know, what do we know? We know there's a threshold fluence for certain, beyond which irradiation effects become dominant. In BWRs, that's around 0.3 to 0.7 displacements per atom. And you can see such a threshold dose in the graph here for the percentage of intergranular stress corrosion cracking as a function on the x-axis of neutron fluence. Remember, neutron fluence is the number of neutrons per unit area, and neutron flux is the number of neutrons per unit area per unit time. So this graph is showing you the percentage of intergranular stress corrosion cracking as a function of the number of neutrons per unit area. And the graph below presents the mechanisms of irradiation-assisted stress corrosion cracking in austenitic stainless steels, and is another useful graph for you to learn in preparation for voicing your own descriptions of stress corrosion cracking, should you be in an exam or should you be in a career in the nuclear industry. And in that graph you can see the several phenomena. Take the bottom left section of that graph there. That shows chromium content and nickel content as a function of the distance from the grain boundary. Now what's happening there is irradiation is giving kinetic energy to the atoms across the material, allowing the formation of chromium carbides. And those chromium carbides nucleate and grow on the grain boundaries. Now without radiation, the operating temperature wouldn't be sufficient enough for those carbides to form. But radiation is giving you that extra bit of kinetic energy, which is equivalent really to an increase in temperature. And that allows the carbides to form and absorb the chromium in the region surrounding the carbides, which in turn causes segregation, because you have a profile of composition, a variation in composition at the grain boundaries. And with segregation comes varying corrosion properties, as the repassivation rates are going to be different, aren't they? Because you've got different chromium contents. A lower chromium content has a different repassivation rate to a higher chromium content. So this is going to sensitize the grain boundaries to corrosion, and in turn encourage intergranular stress corrosion cracking. And that's exactly what you see. Such segregation does have a significant effect on stress corrosion cracking levels, but you can mitigate it. And it's limited by allowing those carbides to form fully prior to you putting it into operation. So you're going to use some thermomechanical processing to homogenize the chromium and nickel profile across the grain boundary, so you don't have any depletion. So you mitigate the corrosion issue. Now, next, sort of on that graph, is our dislocations accumulating along a slip plane. You see just above it, above the bit we were just talking about, you can see these dislocations along the slip plane. Well, here you have the piling up of dislocations along the slip plane, which is causing hardening. But you can also see that hydrogen is collecting And what that's doing is causing hydrogen embrittlement. Now, we could discuss, quite frankly, for days, if not just hours, but it's outside the scope of the course, hydrogen embrittlement, so I won't go into detail. I might upload a lecture on this for you soon, but let's just say for now, hydrogen can cause a higher density of dislocations in a pile-up, effectively enhancing localized plasticity, which can then lead to fast fracture. Should that seem contradictory, congratulations. It means you understood it. Welcome to hydrogen embrittlement, full of contradictions. Feel free to prod my brain on that any time. I researched it for long enough, but you can do that in the supervision. We've got other things to concentrate on for now. Let's continue on this graph. You look to the right of the graph, you see radiation-induced changes in the reactor water chemistry. Well, here we have free hydrogen and oxidants that then cause corrosion. And these species are caused by the radiolysis of water. Now, this radiolysis I've mentioned a number of times previously. It's where water, under irradiation, leads to the creation of various free radicals and oxidants through the following reactions. Top of page 81, you see these reactions listed. They can increase the corrosion rates quite significantly, i.e. they raise the electrochemical corrosion potential. Fortunately, again, you can mitigate the issues arising from these species, and you do so by adding hydrogen to your reactor water. Specifically, you add hydrazine to your reactor water, and that hydrogen, or hydrazine, reacts rapidly with the oxidants and prevents them from causing any excessive corrosion. And that's very effective, but only in PWRs, only in pressurized water reactors. It's not so effective in boiling water reactors. The reason being is, what's the key difference between a BWR and a PWR? Give you a hint, it's in the name. The water boils in the primary circuit in a BWR, and it doesn't in a PWR. Well, when you do get boiling, which in a BWR occurs around 25% up the core, you have then two-phase flow. You've got steam and water. And any hydrogen you've added will boil off and will partition preferentially to the steam phase. So can no longer remove any oxidants in the water. So it doesn't work for BWRs, only PWRs, because of that segregation, partitioning to the steam. So what about, let's think about a sample that's been irradiated, then corrosion tested in a radiation-free environment. Would you still get the same effects? Yes. The irradiation-assisted stress corrosion cracking effects that we've discussed are called persistent effects. You don't need irradiation and corrosion to be simultaneous. Should you take a sample out of a reactor, they will still show irradiation-assisted stress corrosion cracking. And that means that there must be irradiation-induced microstructural changes that are relevant to stress corrosion cracking. And that's what we're going to cover now. And what we'll do is we'll first begin with stress. Because you need a stress in order to have stress corrosion cracking. As we know, the most components will be subjected to a stress in one form or another. And most notably is welds. Welds are a major concern on account of the residual stresses present in and around welds. Now, you'll remember that creep is accelerated under irradiation, and creep is a mechanism of stress relief. Well, then if you have a component under stress and it's irradiated, then actually irradiation-enhanced creep could therefore reduce the stresses driving stress corrosion cracking. And this is what you can see in this graph here. Here at the top of page 82, we have a bolt torqued to 250 megapascals, which is then irradiated with neutrons. And what you see is the stress reducing as neutron dose increases, eventually being under no stress at all, albeit for a very significant dose. So evidently we've got challenging processes here, and modelling how irradiation will affect the stresses is quite evidently very complex and will require the consideration of radiation effects such as swelling, which generate stresses, and irradiation creep, which relieves stresses. But so you're not too confused, irradiation produces more stresses than it relieves, ultimately, and so in the end it almost always enhances stress corrosion cracking in almost all cases. But we've got one more piece to our radiation effects puzzle, and that's segregation. This I have mentioned earlier with respect to the segregation seen in stainless steels on the grain boundaries, so we won't go through that again, but remember that this is not the only case of segregation. We also have the inverse Cakendell effect, which you will recall again for stainless steels, where you've got more mobile atoms, such as chromium and iron. They diffuse away from the voids and lead to the transformation of austenite to ferrite in those regions away from the voids, because they are ferrite stabilizers. Whereas close to the voids, you're rich in nickel. Nickel is an austenite stabilizer. It remains austenitic by the voids. And because of those phase changes, you get different enhancements of corrosion, because ferrite is more susceptible to corrosion than the previous austenite. And all of these irradiation effects can be allocated into the flow chart that I've provided here. So this could be quite useful for your revision, because if you follow the flow chart, it's showing the processes by which radiation damage and its effects occur, which should prove useful for you. You should be able to take a material and explain how each stage in the flow chart occurs for said material, and thus be well equipped to tackle a materials challenge should you ever encounter one in your nuclear career. Presuming I've convinced you to go into nuclear. And really, that's it from me. That's the end. I hope you've all enjoyed these lectures, or found them interesting at the very least. Provided you've listened, you should have little trouble tackling the exam, really. This course is built to prepare you with the necessary knowledge to work in or alongside those in nuclear materials. And it's written to be interesting. We've covered all the key radiation effects in the relevant materials, but as I said, there is much, much more that you can learn, and I encourage you to do so, should you wish to enter into the nuclear industry. It's an incredibly exciting industry, many interesting areas in need of research, with materials science most definitely dominating that research. So there's a lot to do, you won't be short of work. So should you be interested in solving what is widely seen as the biggest challenge to this generation, sustainable energy production, I'd be more than glad to help you find positions, internships, PhDs. You only need to ask me. But thanks for listening. I'm sorry I can't be there in person, but hopefully we'll all be back to normal soon in these strange COVID times. Until then, at the end of your notes, you will see I've included a question sheet for you to have a go at now, and an examples class sheet. And that's full of questions similar to those you should expect in your exam. And I'll upload a video at some point going through those problems, but we'll of course organise some small group supervisions for you to ask me any questions you have on those questions or the course content as a whole. But until then, I hope you've enjoyed the course, and I'll see you all soon.